Hello, welcome to statistical learning session. Today, in this section, we'll explore concept of convergence, specifically uniform convergence as described by Glivenko-Cantelli theorem. We'll then discuss application of central limit theorem to establish asymptotic normality. So let's get started. Now, from the CLT, from Glivenko-Cantelli theorem, we have a convergence. We have convergence. Not only is a convergence, it's a uniform convergence. Initially, we have convergence, then uniform convergence is established by Glivenko-Cantelli theorem. That's given. Now, let's discuss about asymptotic normality. What can you tell me about asymptotic normality? Think about a second. It is related to law of large numbers and central limit theorem. And central limit theorem can be applied to f and t, can apply here because f and t is an average function of fn here. If I go here, this is an average, and therefore central limit can be applied here. F and t function of t represents average of Bernoulli random variables. Now, can you tell me what is t here? Think about a second. T is a Bernoulli random variable, and f and t is the average of that. Hence, by CLT, central limit theorem, Fn, average of Bernoulli random variable, and Ft, the expectation of Bernoulli, leads to a Gaussian distribution with a mean, zero, and variance. Now, we have some variance. Since this being a average and this being a expectation, it leads to some variance here, and we have to find out what this variance is. Now, let Gi be an ID Bernoulli with parameter P. Now, let's do some math here. Let's do some math here. That we would say that let Z be an IAD. IAD is a Bernoulli parameter. Bernoulli parameter P. Now, if this is true, then we have expression here is equal to n xn minus p. This converges to Gaussian is normal distribution with 0 p 1 minus p. We know that. Now, if you know this, then our indicator variable, this one, is a Bernoulli. Therefore, we can say that this also should converge to p 1 minus p. Therefore, by analogy, we'll say that since here we can say that it should be equal to f t 1 minus ft. So we can say that since this is t, and p is a mean of Bernoulli, so this is a ft is a mean of indicator, then we can say that by analogy ft times 1 minus ft should be equal to a variance of the normal distribution. Therefore, we have a Gaussian distribution using CLT with mean 0 and variance of ft 1 minus ft. By establishing uniform convergence, so in summary, by establishing uniform convergence through Glivenko-Cantelli theorem, we laid the groundwork for applying central limit theorem to our analysis. We examine how ft, representing average of Bernoulli random variables, converges in distribution of Gaussian distribution. This provides us with a powerful method to understand behavior of large samples, ultimately resulting in Gaussian distribution with mean 0 and variance ft 1 minus ft. Thank you for today. I will see you next learning session. Thank you so much. Have a nice day.